In the previous video, we have seen that coupled resonators can be used to create bandstop or bandpass filters. In this case, we are using lambda by 4 transmission line sections, open circuited or short circuited as a resonator, and these resonators are connected to each other by transmission line section of characteristic impedance Z naught and electrical length lambda over 4. For the case of bandstop filter, the stubs would be, or the resonator would be, open circuit transmission line. Open circuit resonators has an input impedance Z equal minus JZ naught N, which is the characteristic impedance of the nth stub, cotan theta. And effectively, theta would be pi over 2 at omega equals omega naught, which correspond to electrical length lambda over 4. At theta equal pi over 2, the input impedance in this case would be 0, which correspond to a series resonant LC circuit. So, in this case, the equivalent circuit for the loaded or coupled resonator filter can be represented as the stub will be replaced by series LC circuit in shunt. Then the transmission line section, which has a length lambda by 4, it can be represented as an admittance inverter of characteristic admittance 1 over Z naught. So the equivalent circuit in this case would be L1 C1 followed by an inverter, L2 C2 followed by an inverter, and so on. And here we have the load impedance Z naught, and we have here the input impedance or input admittance. The input admittance of open circuit stub around lambda over 4, around the cutoff frequency, not exactly at the cutoff frequency, what will be the input impedance? As we said, the input impedance of open circuit stub is minus JZ naught N cotan theta. When theta equal pi over 2 at omega equal omega naught, the input impedance would be 0. Around omega equal omega naught, such that omega equal omega naught plus delta omega, where delta omega is much smaller than omega naught, we can approximate theta to be pi over 2 multiplied by 1 plus delta omega over omega naught. We have incremental differentiation of the value of theta in this case. At omega equal omega naught plus delta omega, the input impedance in this case would be minus JZ naught cotan theta, where theta is pi over 2 plus delta omega over omega naught. We can approximate the cotan in this case to be tan pi delta omega over 2 omega naught. And because delta omega is much smaller than omega naught, tan x, where x is very small, is nearly x. So this value is nearly JZ naught by delta omega, where delta omega is omega minus omega naught over 2 omega naught. On the other hand, from the equivalent circuit, the input impedance of such equivalent circuit is J omega Ln plus 1 over j omega Cn. And the resonant frequency is related to the value of Ln and Cn such that Ln multiplied by Cn equal 1 over omega naught square. So we can arrange this equation as j square root Ln over Cn multiplied by omega over square root Ln Cn, which is omega naught, minus 1 over omega multiplied by square root Ln Cn, which is omega naught. So the input impedance from the point of view of the equivalent circuit is j square root Ln over Cn multiplied by omega over omega naught minus omega naught over omega, which can be represented as 2j square root Ln over Cn omega minus omega naught over omega, assuming that the value of delta omega is much smaller than omega naught. Okay. Now by equating this impedance with this impedance, we can obtain that this value equals this value, which means that before equating it, we say that 1 over omega c, 1 over omega naught, 1 over omega naught is square root Ln Cn. So 1 over omega naught can be replaced by square root Ln Cn. So Cn is removed with Cn, and we have Ln squared under square root. So this would be 2j Ln omega minus omega naught. Now by equating the impedance of the equivalent circuit by the impedance of the stub obtained from the transmission line equations, we can say that 2jln multiplied by omega minus omega naught equals jz naught n by omega minus omega naught over 2 omega naught. Or in other words, we can say that z naught n would equal 2 multiplied by 2, 4 omega naught Ln over pi. Okay. So the relation between the value of the characteristic impedance of the stub number n, z naught n, and the corresponding value of the equivalent inductance Ln is that z naught n equal 4 omega naught Ln over pi. Effectively, from the filter prototype, we are going to determine the value of Ln and Cn according to the required specification of the filter. So, by the specification of the filter, we determine the value of Ln, and after we determine the value of Ln, we can determine the characteristic impedance of the transmission line section, which can be used for such result. Okay, so at beginning we are going to determine the value of Ln, and by determining the value of Ln we are going to determine the value of the required characteristic impedance. Now we are going to take just two sections of the coupled resonator filter. We have this is the load, this is the equivalent circuit for the first stub, this is the inverter which corresponds to the transmission line section of length lambda by 4 between the two stubs, and this is the second stub. The input admittance of such circuit can be obtained as follows. The input admittance Y is the admittance of the first section, which is 1 over j omega L2 plus 1 over j omega C2. This is the admittance of the first branch. Then the admittance seen from the inverter. The admittance seen from the inverter equals j squared, which is 1 over z naught squared, over the admittance seen or the input admittance of the filter. The input admittance of the filter is the admittance of the first stub 1 over j omega L1 plus 1 over j omega C1 plus 1 over z naught. By arranging this equation, we can obtain the total input admittance is given by 1 over j square root L2 over C2 multiplied by omega over omega naught minus omega naught over omega, and it should be kept in our mind that omega naught equal 1 over square root L2 C2 and also equals 1 over square root L1 C1, okay, plus 1 over Z naught multiplied by 1 over J square root L over C1 omega over omega naught minus omega naught over omega plus 1 over Z naught. This should be to the power minus 1. This should be to the power minus 1 or not. This should be to the power minus 1. Okay. On the other hand, if we are talking about the prototype filter for the band stop filter, would have a series tank circuit composed of parallel LC circuit, which is L1 C1 in parallel to another tank circuit composed of series resonant circuit L2 C2 So this is the circuit or the prototype circuit of band stop filter. For such a prototype circuit of band stop circuit, the input admittance is given by the input admittance of this branch composed of L2 dash C2 dash, which is 1 over J omega L2 dash plus 1 over J omega C2 dash plus the admittance of this branch. The admittance of this branch is effectively 1 over its impedance. So the impedance of this parallel LC circuit, which is 1 over J omega C dash plus 1 over J omega L dash plus Z naught, all of this is to the power minus 1. 1 over square root L1 dash C1 dash should equal omega naught. And similarly, 1 over square root L2 dash C2 dash should equal omega naught, where omega naught is the center frequency of the proposed stop band. Okay? So we can arrange this equation as J square root L2 dash over C2 dash multiplied by omega over omega naught minus omega naught over omega plus 1 over J square root C dash C1 dash over L1 dash omega over omega naught minus omega naught over omega plus Z naught to power minus 1. So this is the input admittance of the filter prototype of band stop filter, and this is the input admittance of the coupled resonator structure composed of open circuit resonators connected by transmission line section of length lambda over 4. It can be seen that the main structure of the input admittance in the two cases is the same. This means that this circuit, it can be equivalent to this circuit. Or in other words, this circuit, it can be used as a band stop filter. And to be used as a band stop filter, we should equate every term in this equation to the corresponding term in this equation. So, for example, in this case, square root L2 over C2 should equal square root L2 dash over C2 dash. And 1, I believe that this 1 over Z naught squared this should be squared. One over Z naught squared multiplied by this value to the power minus 1. So this value should equal this value with this factor. Let us see. That's what I'm seeing here. It is required to equate every term in this side to this side. So the first term is L square root L2 over C2 equals square root L dash L2 dash over C2 dash. And one over Z naught squared multiplied by this bracket to the power minus 1 correspond to let us see that Z no 1 over Z naught square root L1 over C1 should equal square root C1 dash over L1 dash. Okay, so we have two relations now between the value of the capacitance and inductance of the filter prototype and the capacitance and the inductance of the resonators. By using these two relations, we can find out the relation between the inductance of the stub L1 in terms of the inductance of the filter prototype L1 dash and the inductance of the second filter or the second resonator L2 in terms of the inductance of the filter prototype L2 dash. So by solving these two equations and taking into consideration that Ln multiplied by Cn, where n is 1 or 2, equals Ln dash Cn dash equal 1 over omega 2 square, omega naught square. So by applying this equality in these two equations, we can obtain the relation between L1 and L1 dash and L2 and L2 dash. And we have previously shown that there is a relation between the required characteristic impedance of the resonator and its equivalent inductance, such that Z naught N, the characteristic impedance of the stub N, equal 4 omega naught multiplied by the equivalent inductance of the resonator Ln over pi. So by using the filter prototype, we can determine L1 dash and L2 dash which satisfy the required specification of the filter. And from L1 dash and L2 dash, we can determine L1 and L2 which correspond to the value of the inductance for the resonators or the required resonators. And from L1 and L2, we can obtain the characteristic impedance of such resonators, of such coupled resonators. So by applying this relation, in this relation, we can obtain the required characteristic impedance for the first resonator. It would be 4z naught square over pi omega naught L1 dash, and the characteristic impedance of the second resonator would be 4 omega naught L2 dash over pi. And actually, the value of L1 dash and L2 dash are determined from the filter prototype in terms of G1 and G2, as L1 dash is G1 multiplied by Z naught multiplied by delta over omega naught. So by inserting the value of L1 dash in terms of G1, Z1 naught, it would be 4 Z naught over pi G1 delta, where G1 is the first element of the low pass filter prototype. and Z node 2, the characteristic impedance of the second stub, would be 4Z node over by G2 delta. In general, Z node N for N stubs would be 4Z node by over Gn delta, because effectively this is the same relation for the first stub and the second stub, and actually this is generalized for any stub in the coupled stub resonator filter. So in coupled resonator filter, the characteristic impedance of the resonator N is given by 4Z node over by the value of Gn of the prototype multiplied by the delta, where delta is the fraction bandwidth of the bandstop filter, which is omega 2 minus omega 1 over omega naught, the fraction bandwidth of the filter. This analysis was done for open circuit stubs or open circuit resonators, which can be used to implement bandstop filter. Similar discussion can be obtained for short circuit resonators, which can be used to band pass filter. In this case, for the band pass filter, by using short circuit stub resonator, the corresponding result for the characteristic impedance is Z naught N would be by Z naught delta over 4Gn. So this is the characteristic impedance for open circuit stub for the case of bandstop filter. This is the characteristic impedance for short circuit stub for band pass filter. And it should be noted that the present analysis is based on the load impedance. It should be Z naught, or as a normalized it should be 1. So in the case of Chebyshev filter, this analysis is only valid if the value of n is even. The value of n is odd, such that for the n odd we have the load impedance is 1, and for n even the load impedance is not 1. So these results only apply for filter having input impedance of Z0, so cannot be used for equal ripple or Chebyshev filter with n even. Must be n odd in this case for Chebyshev filter. As an example, it is required to design a bandstop filter using 3/4 wave lambda by 4 open circuit stubs. The center frequency is 2 GHz and the bandwidth is 15%. So this is F naught and this is delta F. And the impedance is 50 ohm using equal ripple response with 0.5 dB ripple level. We have 3/4, so we are talking about n equals 3. From the table of 0.5 dB Chebyshev filter, we have the value of G1, G2, G3, and G4 is 1, or the load is 1. From the values of the G, we say that the required characteristic impedance for the stubs is given by Z0 N would be 4Z0 over by Gn delta. Z0 is 50 ohm and delta is 0.15. So by applying these values, we can obtain the required characteristic impedance of the first stub, second stub, and third stub. From these values of the characteristic impedance, we determine the width of each stub. On the other hand, the length of all stubs are equal, which is lambda by 4. So we calculate epsilon effective for each transmission line section of this characteristic impedance, and we have lambda by 4 transmission line sections, open circuit stubs with these characteristic impedance. And these stubs are connected by transmission line section of impedance 50 ohm. So we have 50 ohm and the first stub 50 ohm and second stub 50 ohm and the third stub 50 ohm and the input port. Okay, all right. This is the response of the design bandstop filter, and as I said before, has sharp behavior around the required bandstop.